research aim to make sensitive polarization measurements of the cosmological method for work. So mostly focused on instrumental development and characterization for these two experiments. And it's great to see her here. So I'm going to give her a quick hand. Thank you very much.
Thank you. Thanks, everybody. Thank you for coming here. Thanks for having me. And yeah, if you guys have questions, if it's a quick thing, I'm happy to answer during the talk, but maybe if it's a more detailed question, we can wait until the end. Yeah, so let's get started. So today I'll eventually get to the question about what can we learn from the cosmic microwave background polarization. But before I get there, I'll give an overview of how we understand the early universe was, what is the cosmic microwave background, talk about some features of the CMB, which, yes, in this talk, if I say CMB, it's the cosmic microwave background. Then I'll discuss some open questions in cosmology and how the CMB polarization can help us explain them. And then I'll give just a brief touch of flavor on what CMB telescopes might look like at the end. So yeah, let's get started talking about the early universe and the CMB. So back in 1929, almost 100 years ago, Edwin Hubble, yes, the guy whose telescope was named after this guy. He noticed that stars moving away from us, the stars that are far away from us move away at a speed higher than the ones that are close to us. This is what is shown on this plot, where he shown the velocity of stars as a function of how close they are to us, and the ones that are further away are moving away faster. This was the first evidence that the universe is expanding, and we've seen a lot of more of that evidence since then. The fact that the universe is expanding means that if we go back in time, it was much smaller, denser, and hotter. This figure is something that you might see anywhere or anytime someone's talking about cosmology. It's actually at the entrance of Campbell Hall, and it's our description of the universe timeline, essentially that it has been expanding for the past almost 14 billion years. And we think that at the very beginning, there was a period of inflation where it extended really fast, but even since then, it kept expanding. And we'll get to talk about inflation later on in the presentation. What we care about today is talking about this afterglow light pattern that started propagating around the universe around 400,000 years since the Big Bang. Let's talk about the early universe. So in the first few 100,000 of years, the universe was this hot plasma. So we had matter that was completely ionized. Because of this, light particles or photons were strongly interacting with the free electrons via Thomson scattering. They're all scattering on each other. As a consequence, light and matter were strongly coupled and in thermal equilibrium. As the universe expanded, it also cooled down, and that allowed neutral atoms to form. So instead of having the free electrons, now we have electrons that are bounded to protons forming neutral atoms, and the photons don't have any more free electrons to scatter from, and they start to free propagate. They're pretty much free to propagate until they reach essentially us, our telescopes. They don't really interact with much else since then. And these photons are what we call the cosmic microwave background. So let me go back to this picture here. The CMB started free propagating around 400,000 years after the Big Bang. after that, we had these neutral atoms and nothing was really emitting light. So we have what are called this dark age. There's nothing emitting light. That was the case until first stars formed and then they started shining again. And that happened around 400 million years since the Big Bang. And following that, you had first galaxies forming around 1 billion years after the Big Bang. So if you guys know about the James Webb Telescope, the James Webb Telescope is looking for the first galaxies, so around 1 billion years in the cosmic time. The CMB started propagating way before that, so hundreds of thousands of years compared to a billion years. It's like much older than galaxies and stars. It is as far as we can go back in time to understand the beginning of the universe. I wanted to talk about some interesting features of the CMB. The most notable one is that it has a black body spectrum. Why is that? Well, at the time of recombination, I just told you that matter and light were strongly coupled together. So everything was in a thermal equilibrium, and they were at around a temperature of 300,000 Kelvin. Because the universe expanded by a factor of roughly 1,000 since then, we actually measured the temperature of the CMB today to be 2.7 Kelvin. And yes, because things were in thermal equilibrium prior to the photon decoupling, we get a black body spectrum, which is actually the most perfect black body spectrum that we can measure in nature, is the CMB. This plot here is showing the CMB intensity as a function of frequency, and it comes from the Farias instrument that was deployed on the COBE satellite mission back in the 90s. I wanted to just take a quick pause here to talk about COBE, because the work done by the scientists in COBE led to 2 Nobel Prizes. One of them was awarded to James Matter, who did his PhD here at Berkeley back in the 70s. The other day, I was browsing through our cosmology library in the office, and I actually found his thesis, and it's now just sitting on my desk. It's like really cool. The other person who was awarded the Nobel Prize was Professor George Smoot, who was Berkeley faculty. Fortunately, he actually just passed away last week, but I wanted you guys to know of the legacy that Berkeley has on cosmology via CMB work. It's very impressive. Oh, come back. No, I didn't do that. No. Another interesting thing about the CMB is that anywhere you look in the sky, you see the black body spectrum, you see the 2.7 Kelvin temperature of the CMB, like anywhere in any direction. Except that if you start to make more and more accurate measurements of the CMB temperature, you start to see very, very small fluctuations on this temperature. These fluctuations in the CMB temperature are a consequence of small variations in the plasma density at the time of the photon decoupling. So you can imagine you have this hot plasma, but it has over densities here and under densities there. And because everything is coupled together, light and matter, you actually see the effect of that through the temperature of the CMB. This map that I'm showing here is from the Planck satellite instrument, satellite mission, which is the latest satellite to look at the CMB. And one important feature is the size of these temperature variations. We also call them anisotropies. Remember, the CMB temperature is something like 2.7 Kelvin. The variations are in the order of a few hundred microkelvin. It's much smaller than the actual temperature of the CMB. Another interesting thing about these temperature fluctuations is that they're correlated. So CMB scientists look at the map of the CMB and they essentially do what is equivalent of a Fourier transform in spherical coordinates and trying to find the correlation between hot spots and cold spots around the entire sky at different angular scales. And the result of that is plotted as what we call the power spectrum, which is shown here from also the Planck satellite mission. The most prominent feature of the CMB power spectrum are these large peaks that come from sound waves also at the time of recombination. So you have this hot plasma and you'd have this interaction between light and matter because light has some pressure from the photon particles and the matter content pulls things back and forth due to gravity. So you end up with these acoustic oscillations from the combination of light pressure and gravity from matter forming these acoustic oscillations, and that appears in the CMB power spectrum as these peaks. And you might notice that these data points from Planck, they have extremely small error bars because we can measure this so precisely and they're like very defined features of the CMB. And in this plot, what is also shown is this blue curve, which is the best fit to the lambda CDM model. So let me talk a little bit about the lambda CDM model. I'm going to do a little digression here. The lambda CDM model is the standard model of cosmology. In the same way that particle physics has its own standard model, the lambda CDM model is our best model of like how the universe has been evolving over time. We make some key assumptions. One of them is that physics is the same everywhere. So if I measure something here and I go to a faraway galaxy and I do the exact same experiment, I should get the same result. Physics is the same everywhere. On large scales, the universe is statistically the same. So if you look away from our solar system or galaxy or even our galaxy cluster where we're at and look far enough away, statistically, it's pretty much all the same everywhere you look. It also assumes that general relativity is an appropriate description of gravity, and that the universe is made of 5 basic ingredients. We have atomic matter, like electrons and photons, and just things that we interact with, and the things that we can see in our particle accelerators here on Earth. But we also have dark energy, which we don't really know what it is, but it affects the expansion of the universe. There's dark matter, which we also don't really know what it is, but it has gravitational effects like normal matter, we just can't see it. It has photons, light, and neutrinos, which I'll also talk about later. The other assumption is that the curvature of space is small, and we'll also get back to that in a second, and that the variations in density, so those like small fluctuations in density that we had in the hot plasma, were laid down at a very early time everywhere. Now, back to the Planck measurement. I've shown here the plot from the power spectrum from Planck. And what we see is this incredible agreement between our lambda CDM model and the measurements from the CMB. You see how tiny those error bars are, and you see how well that fits on that curve. That is an impressive agreement between theory and measurements. It's saying that we understand our cosmological history very, very well. In fact, the CMB measurements alone have constrained 5 out of the 6 free parameters in the lambda CDM model with less than 1% uncertainty. The other parameter that is not less than 1% is like 3%. So we also know it very well. And it's pretty amazing that we can get these like super precise measurements of our large scale behavior. All right, Nicole, you told us a lot about the CMB and the CMB temperatures, but you told me that this was talk about the CMB polarization. So what's up with that? Let's talk about the polarization. First of all, I'm talking about light polarization, not, political polarization or anything like that. To be clear, unpolarized light happens when the electromagnetic wave that might be propagating your light has an equal amount of electric field in all directions. It has no preferred plane of propagation. But when you have polarized light, it has a preferred plane. So the total electric field of that light will be in a single plane of propagation. I won't get into too many details on this, but what we know is that if you have Thomson scattering, so scattering of light and electrons, we can get polarized light of the CMB at the time of decoupling if you have a pattern that looks something like the one on the image here, which is if you have a cold photons approaching an electron and hot photons approaching from a perpendicular direction, you can get an outgoing scattered light that has a polarized component. Now, the CMB polarization, because we only get it if we have these like particular interactions in the Thomson scattering, they are much weaker than the actual TMB, than the actual CMB temperature anisotropies. So this is another plot from Planck, where the colors are still showing the temperature anisotropies. It's just a coarser scale here. And again, they vary from a few 100,000 microkelvin plus or minus, but the lines on the plot are indicating the polarization patterns, and these have a much smaller magnitude, as indicated by the scale there. The little trace is less than a microkelvin of magnitude. So polarization signal is much weaker than the actual variation in the CMB temperature. CMB folks like to divide the polarization patterns into two types. One of them is called the E mode, because it remembers like an electric field. It has no curl, and it can be sourced by those density fluctuations that we talked about. And because of that, it is a stronger signal, and that is what is shown on the top of the figure there. The B modes, on the other hand, have no divergence, and they cannot be sourced by density fluctuations, and as a consequence, they are a much weaker signal, and that's what's shown on the pattern type is shown at the bottom of the figure. All right, so what does the polarization actually tells us? There's a lot, and I will not get into all of the details, especially on E modes. I won't cover this too much, but one thing that we can find from E mode measurements is this parameter called the optical depth, often written down as tau, is one of the 6 pre-parameters of the lambda CDM model. And it measures how often CMB photons have scattered since the universe became ionized again. So ever since we had first stars, those photons started to interact with free electrons again, and that's what the optical depth tau parameter tells us. But I won't discuss it in any detail. B modes, on the other hand, are interesting and are the thing that people have mostly been focusing nowadays. And they tell us information about the sum of neutrino mass and whether or not cosmic inflation happened. And I put it in blue because people were very interested in answering this question.
Yep. Can I ask, was the optical depth the one parameter that was greater than 3%? Or
It
like
is.
greater than 1%? Okay.
It is, yeah.
So that's
Oh, I'm sorry. Joseph asked if the optical depth is the parameter that hasn't been constrained to less than the percent precision, and yes, it is. Okay, so the polarization can tell us about these things, but why is that important? Let's talk about neutrinos first. So neutrinos are these very tiny and neutral particles. They're so small that so far no one has actually been able to measure how much they weigh. The CMB is sensitive to the mass content of the universe due to gravitational lensing, which I'll talk about in the next slide. But the idea is that because the neutrinos contribute to the total mass content of the universe, if we can measure the actual amount of mass in the universe with the CMB, we can have an idea on how much the neutrinos are contributing to it. And we can do that because of the effect of gravitational lensing. This effect occurs because gravitational fields can distort the path of light. So anytime you have anything that is massive and light goes near it, it would actually get deflected due to, general relativity. This happens in, for example, galaxy clusters, and this picture here is an illustration of that. It's a photo taken from the Hubble telescope, where you see that the galaxies are kind of like distorted, they're kind of like squished out. And it's not because they are physically like that, it's because the light coming from them gets distorted by the galaxy cluster, so it looks to them like they're squished. The same effect that can happen with CMB photons, and that results in E modes, which were generated by density fluctuations to be converted into D modes. And the amount of this conversion can tell us how much mass the CMB photons actually interacted with, and is a measure of the mass content of the universe. All right, so what about inflation? I'm going back to the picture at the beginning here. I told you that we think there was a period of rapid expansion that happened very early on in the universe. This period is called inflation, and we haven't confirmed yet if it existed or not, but there's good reason to believe it did. And if it did happen, it would mean that the universe expanded like incredibly fast, from like, 10 to the 4 times 10 to the negative 29 meters to like a meter in a fraction of a fraction of a fraction of a fraction of a second. Very fast. The reason why people think inflation happened is because it can explain a lot of open cosmological questions. The first question is the horizon problem. I told you that anywhere you look in the sky, the CMB looks the same. But given the amount of time the universe has existed, almost 14 billion years, we actually don't expect that all regions in the sky to be causally connected. In fact, only things that are separated by 2 degrees in the sky should have been in causal contact at the time that the CMB got decoupled. So we don't understand that without inflation. The other question is, why is the universe flat? And by flat, I mean, with general relativity, we understand that if you have mass, the mass gravitational field distorts space. It can give curvature to space. But in large scale, when you look at the whole picture, our universe, as far as we can tell from CMB measurements actually, is flat. It has no curvature. And we don't know if that's a coincidence or not. The other thing is, I told you guys that we have these fluctuations in the density of matter in the hot plasma, but what actually seeded those inhomogeneities. Inflation can solve the horizon. Oh, yeah, Drew.
Sorry, I have one more. So, like, what would what would it mean if the universe wasn't flat? Like, would everything be like gravitationally pulled to like a single point, or what is that? What is, or is that not a good question? Like, what would the universe look like if it wasn't flat? Maybe that's kind of hard to conceptualize.
Yeah, it is kind of, the question is, what would the universe look like if it was not flat? I don't know that I have a good picture of what it would look like. Yeah, maybe we can talk about that later.
Yeah.
I don't have a good picture that I can say right now.
Just think of what you mean by flat. Do you mean like this, as in everything moves in essentially this plane?
It's flat in 3 dimensions.
Oh, you mean I guess the curvature is essentially.
Yeah.
Okay.
Other questions? All right, so yeah, inflation helps solve these problems. First of all, because it decreases what's called the comoving horizon. The comoving horizon is how far can particles travel and still be in causal contact with each other. The idea is that at the beginning of inflation, or before inflation, the comoving horizon was very large, meaning you could travel a long way and still be in causal contact with other particles. But because everything expanded, that horizon decreased until inflation ended, and then the standard hot Big Bang time started, and things were able to get into causal contact again. And this is kind of the high level picture without getting into a lot of like GR, but we like it because it solves our horizon problem. What about the other questions? So inflation can explain why the universe is flat, because again, because the universe would expand to such large scales that if there was an initial curvature at some point, it just got extended out, and now we see it as flat. It's similar to being an ant on top of a balloon, and as the balloon is small, you can experience the curvature of the balloon. But as you expand it more and more, you look around and it starts to look like things are flat. So inflation can help us with this flatness problem. It's not that the universe has no curvature, is that it had at some point, but then it got extended out and now we don't see it. And lastly, if inflation happened, then the density fluctuations that we see in the CMB and that seeded all the structure that you see in the universe today could have been sourced by quantum fluctuations. And let's go back to how this actually relates to the CMB. Inflation models predict that they predict the existence of primordial gravitational waves. I again won't get into like all the details of this, since this involves a lot of GR, general relativity. But the idea is that you can have a primordial gravitational wave leading to perturbations of your space-time metric, and the perturbations affect the free streaming of your photons and end up generating both E modes and B modes. Because E modes have large contributions from scalar perturbations, measuring these other perturbations from primordial gravitational waves would be difficult, but B modes don't get sourced by the other type of fluctuations. So if we can measure this effect on B modes, we could confirm if inflation happened. All right, so great. How do we actually do that? I'll tell you that measuring B modes to search for inflation requires very sensitive telescopes. So remember this figure on the left here from Planck, where I showed you that the temperature fluctuations of the CMB are very small, order of hundreds of microkelvin. The polarization that we can measure is orders of magnitude smaller than that. And that is the E mode polarization. So the plot on the right is showing the power spectrum. It was made by the Lightbird collaboration, but the main thing that I wanted to show is that there's three main lines. The top line is the temperature fluctuations power spectrum. So similar to that Planck plot, it just kind of has been squished. Orders of magnitude smaller than that is the contributions is the magnitude of the power spectrum for the E modes. And orders of magnitude smaller than that are the fluctuations coming from the B modes. So this B mode signal is very, very, very small. To make matters worse, the CMB is not the only light in the sky, and not the only microwave light in the sky. We actually have radiation coming from synchrotron radiation and from thermal dust that can contaminate our CMB measurements. They are called foregrounds. And if you want to actually measure the CMB signal, we need to properly characterize these foregrounds and filter them out of our measurements. So the plot here, is showing the brightness of each component in each polarization component. And the CMB, you can see, is like weaker than the other two. So we need to understand them, and to understand them, what is required is measurements at various different frequencies, so that we can make a model of the foregrounds and remove them from the data. These measurements are hard, but there are a lot of active experiments trying to make them. I'll mention a few of them here. So Simon's Observatory, South Pole Telescope, and Lightbird are really cool experiments that have Berkeley's faculty actively working on them. So that's very cool. There are other experiments like BICEP and CLASS that also exist and have been working on them, and other experiments and more. So there are many collaborations trying to get these measurements. I personally worked on an experiment called Simon's Array, which was already decommissioned, but was located in the Atacama Desert in Chile. You might notice that these telescopes have interesting location choices. Some of them are in the Atacama Desert, some of them are in Antarctica, and Lightbird will go to space. Why do we pick these locations? The reason is that water in our atmosphere gets in the way of our CMB measurements. So we want to place our telescopes in a place that is as high and dry as possible. The best place is obviously space. There is no water in the vacuum of space. So if you can go to space, that sounds great. But it's obviously also very expensive, which is why we don't have as many experiments in there. The Atacama Desert is the driest non-polar desert in the world, and it also has huge volcanoes. So we can put our telescopes as high as 17,000 feet of altitude, which is 5,000 meters. This is a picture of me and Professor Adrian Lee, who was my thesis advisor, working on commissioning Simon's Array. We have these tubes in our faces because we are at such a high altitude that if we don't have them, we'll just suffer from altitude sickness while trying to do work. And yeah, the other location is the South Pole, which has also one of the driest deserts in the world in the Macardo Valley, which is also extremely dry and cold. And finally, I just wanted to give a small taste of what an instrument might look like. Measuring these extremely small signals require that we do cryogenic measurements. The idea being that if you operate things at low temperature, you get a lot less noise. And CMB experiments use superconducting detectors that are usually operating at less than 1 Kelvin, so very, very cold. This is a CAD image from one of the Simon's array receivers, just to show a little bit what the instrument might look like. It has these aluminum lenses that are cold at 4 Kelvin. We have our detectors in our focal plane at a temperature of 250 millikelvin, and we have cryogenic readout electronics that are also at 250 millikelvin and 4 Kelvin. I'll say that cryogenic measurements are difficult, and there is a lot of ongoing work to develop the hardware for these instruments. That has been most of my PhD work. And yeah, there's a lot of advances in the field that people have been working on. And yeah, we reached the end of my talk. So as a summary, measurements of the CMB polarization inflation can tell us a lot of different things. I think the thing that people are mostly excited about is searching for inflation. We want to show that it happened because it helps us explain our cosmological history. But we can also learn about neutrino masses and the ionization optical death. There are other things that I didn't bring up on this talk, but it is really a rich field, and you can do a lot of cool science with it. Yeah, there are many people working on these measurements and data analysis. And if you're undergrad and you're willing, you could too. I'll say that I'm graduating soon, so I won't be mentoring new students, but if you are interested in the field and you just want to talk to someone that has worked on it, I'm happy to talk to you guys. So yeah, just email me or come talk to me after class. Yeah, that's it.
There's going to be some questions I'd love to take. I just want to remind people, because I forgot to do it earlier, if you came in late, please sign in for us to just get reimbursed for all the snacks and stuff. There's a sign in QR code, I think, over on the table. So when you go get your refill of snacks, just please put that down. But while people do that, it would be great to have some questions for Nicole. Does anyone have any questions?
I'm sure.
Do you have any advice for if you're interested in doing PhD level work in cosmology and how to position yourself from like the junior level to there if you're not necessarily in astrophysics?
I mean, Nicole, where'd you come from before you were a physicist?
Yeah, the question is if I have advice for someone who's interested in doing PhD work in CMB cosmology. I mean, there's so many things that you could be working on. There's people that are very focused on data analysis and are great at, coding, or if you're more of a hard work person, I did my undergrad in mechanical engineering and I joined the lab to do a PhD in physics, and I was able to apply a lot of my knowledge on the hardware development. Advice, I mean, if you're willing and you want to get involved, I think talking to people that work in the field and seeing what they're working on and understanding where your skills might fit that, and if you think you want to develop more skills to be better prepared to work on it, then you can do that if you have time. Yeah.
In the beginning of your conversation, you're talking about how the universe has just a hot plasma. But at the beginning of the universe, it's an organized gas. So what organizes it, or what's the idea of that plasma in the beginning?
The question is,
I guess, like, what organizes the plasma? If plasma is a hot ionized or an organized gas. Like, is there something, or an idea of what's supposed to be producing fields that?
The question is, what is organizing the initial hot plasma? It's disorganized. It is just if you make something hot enough and dense enough, it will ionize. So just the fact that everything was compressed together, the universe was like smaller and hotter, you have like a lot of energy, led to the existence of the plasma, but it was a disorganized gas. Yeah.
You had that slide on the lambda part. I'm just curious, whether lambda makes any assumptions about the nature of dark matter and dark energy, or does it just need like the mass distribution in the universe? And that's the only one.
Yeah, good question. The question is, if the lambda CDM model has assumptions about dark energy and dark matter. Right. So the C comes from cold. So one of the assumptions is that dark matter is cold. I can't remember exactly how that like what that means specifically, but I think there's a threshold on the mass of dark matter particles that makes them cold. So that was one of the assumptions. And for dark energy, is there an assumption on it? I guess it's something that doesn't behave like matter as we know it. People often call it vacuum energy because it just comes from nothing. Yeah, but we don't know much about it. That's a good question though. Yeah.
Kind of more of a question on the neutrino mass related stuff. So I guess the first part is, what are the like current upper bounds of like that people are able to put on the neutrino masses from CMB? Like I'm not sure I really did that one. No.
Yeah, no, that is a good question. I don't have the numbers from the top of my head. I'd have to look them up. Yeah.
The other part I was wondering is, people that maybe do that kind of work related to neutrinos and CMB. Is it primarily for understanding bounds on neutrino masses, or is it also like, is there a way this goes into investigating why like the mass mechanism of neutrinos is notably different than like other electrons?
Right. So the question is, whether if people working on cosmology and neutrinos, if they're getting more of a bound on the masses, or like understanding why they're small or how they behave.
Yeah, like why, like whatever mechanism is producing the neutrino mass makes them so small compared to like.
Yeah, okay. So whether the mechanism for making neutrinos makes them much less massive than other particles. As far as I know, most of the work is just setting up the bounds on the mass. But maybe there's people that work on that. Yeah.
I just wanted to make sure I understood your answer to this question. The reason for it means the cosmic microwave diagram, all the particles are all together. Was that because space in general was just not big enough? Okay.
Yeah, that's right.
If it were not, I guess that inflation is an assumption. If inflation did not explain the universe as it is there another explanation, or is that basically the reason it's the leading explanation? It just doesn't make too much sense, even though we haven't proved it.
Yeah, so the question is essentially, are there alternatives to inflation? Okay, and why inflation is the leading explanation? I personally haven't seen an alternative explanation. It's kind of like if inflation didn't happen, then we need to start like go back to the whiteboard and yeah, rethink our understanding. There's not other competing alternate theories that have the same advantages as inflation. I'm sure there's always, alternative theories, but I think they're way more nuanced and more complicated, and people don't really bring them up usually.
I guess I'll also just go back to this question earlier. Like, I guess when you say flat expansion, basically, the way I see it in my mind is kind of like that photo you had in your slides where it's like flat, but it's more or less 3D, and then just keeps going up horizontally. Does that make sense?
Yeah, I think that's a good picture. Yeah, it's something that I struggle visualizing myself, to be quite honest.
Yeah.
Hey, in the instrumentation that you're developing, what are the parts of it that are the main sources of noise in your effect? And what are the ones you're working the hardest on to decrease the noise background to make your measurement sensitive?
Okay. Yeah, the question is, what are the main sources of noise in our measurements that we're trying to decrease? There's been a lot of good development on the detectors themselves to make them what is called photon noise dominated, so that most of your noise actually comes from the CMB photons themselves. And that makes it so that the next thing that you need to do to decrease noise, I would say, if you're already operating at cold temperatures, is make your readout system less noisy. So you would have electronics that you need to get the signal to and from your detectors, and that carries noise. That was an issue that we saw in Simon's array, was our readout noise was more elevated than it should be, and we worked hard to try to make it less than that. So that is one thing that people have been working on. And on Lightbird as well, I did a lot of work trying to improve the noise performance of the readout electronics so that it is not larger than the photon noise. Yeah.
So, you literally showed that really like clean fit to the power spectrum for lambda CDM. Are there any astrophysical observations that don't agree with lambda CDM?
That is a good question. The question is, are there any astronomical observations that don't agree with lambda CDM? Do you know any? But it's tension on the value of the parameter, not if the yeah. Yeah, there is something called the Hubble tension, which is that the rate of expansion of the universe is called the Hubble constant, and CMB measurements have a value for it that we get from our CMB observations, but people doing experiments with supernovas, they're measuring supernovas far away from us, measure a different value for the expansion of the universe. So there's a tension there. Yeah, that is one of the things I can point you to.
So does lambda CDM have prediction for Hubble?
I think it's one of the free parameters, isn't that right?
I know we measure precisely for this.
Right, but I think it's one of the 6 parameters. I think it's a free parameter. Pretty sure. I can double check, and if you want to ask me later on, I can double check that for you. Correct. Yeah.
All right, great. It's 4. I'm sure that if people have more questions, they can ask the phone. She'll take some after the talk. But let's give her one last time on hand.